Hi students, welcome to Sunil's tutorial. I'm Sunil Madhwani and today we'll be doing this chapter called as electrostatics. We'll try to find out the electric intensity at a point outside a charged conductor. Electric intensity at a point outside a charged conductor. Now, let's first draw a charge conductor. Now, let's consider this is my center of the charge conductor. This is the center line. This is the radius of the charge conductor. Now, let's consider a charge cylinder of radius r. Consider a charged cylinder of radius r. Let's consider radius as capital R. Let's with a charge of plus q. Charge plus q per unit length. Right? Now let's consider that there is a point P at a distance of r from the center of the cylinder. This distance, let's assume, is r. So you will say that consider a point P. I want to find out how much is going to be the electric force at this point P. So consider a point P. Consider a point P at a distance. Consider a point P at a distance of r from the axis of cylinder. Right? Now, in order to find out how much is the electric force at this point, we will draw a Gaussian surface. So let a Gaussian surface in the form of a, what will the Gaussian surface be? The Gaussian surface is always same as the given body. So whatever is the shape of the given body, the Gaussian surface will also have the same shape and it will be an imaginary surface. Now since my given body is a cylinder, my Gaussian surface will also be a cylinder. So I'll have a cylinder of radius r. I'll have a cylinder of radius r. Right? Let's assume that the length of this cylinder is 1. So you will say that consider a Gaussian surface. Let a Gaussian surface.
So is it compulsory to assume the same?
Yeah, whatever the figure, the Gaussian surface will also have the same shape.
I mean, like, can't we assume a circular?
No. The Gaussian surface will have the same shape because electric intensity is same inside and outside the conductor. Remember, what does the Gaussian theorem say? That whatever is your form of conductor, you will have the same electric intensity inside and outside. Right? So we assume this to be the core, the inner part of the conductor, and this to be the outer part of the conductor. Right? So let a Gaussian surface in the form of an imaginary coaxial cylinder of radius r. Cylinder of radius r and length L. Be drawn around cylinder AB. Right? Now, point P therefore lies on the surface of the cylinder. I can say that point P lies on the surface of the cylinder. Once I know that point P lies on the surface of cylinder, since you do not have tubes of induction perpendicular to the plane faces, see, this is my charge conductor. if this is my charge conductor, the charge will move outwards. If it is going to move outwards, it is going to move through the curved surface of the cylinder, Gaussian surface. It will not move through the plane surface of the Gaussian surface. Do we understand this? Since the Gaussian surface is circling the conductor, the charge that will be given out from the conductor will move through the curved surface of the Gaussian cylinder and will not move through the upper and the lower plane surface of the Gaussian cylinder. So I can say that since there are no tubes of induction, perpendicular to the plane faces, of the imaginary cylinder, the total normal electric induction over the plane faces will be zero. Over the plane faces will be zero, right? So there will be no lines of force passing through the plane faces. All the lines of force will pass through the curved surface. Now, the electric intensity at all points on the cylinder has to be the same. The electric intensity at all points, on the cylinder is the same. Therefore, I can say that moreover it is these electric intensity that is going to be given out from the cylinder will be perpendicular to the Gaussian surface. These lines of force will move outwards. These lines of force will move outward and they will be perpendicular to the curved surface area of the Gaussian surface. So I can say, and moreover it is perpendicular to the surface. Right? Therefore, the total normal electric induction over the curved surface, is going to be over the curved surface, and it is going to be given by epsilon E into the area of the curved surface right? That's my formula for total normal electric induction, epsilon E into area of the curved surface. Now in the case of this is going to be epsilon E curved surface area. Curved surface area of a cylinder is 2 pi RL, right? Now, what is the total charge that is enclosed inside the imaginary cylinder? The total charge enclosed inside the imaginary cylinder we have said that the charge per unit length is Q and the total length of this cylinder we have assumed as L. So the total charge in the Gaussian surface curved surface area is going to be QL. Q is the charge per unit length of the Gaussian surface is L. So this is going to be QL. Now if I apply Gauss's theorem says that the total normal electric induction should be equal to the total charge enclosed in the cylinder. Total normal electric induction will be QL. We said that total normal electric induction is epsilon E 2 pi RL. Therefore, I can say that epsilon E 2 pi RL is going to be equal to QL. L and L gets cancelled, in which case I can say E is equal to Q upon 2 pi epsilon R, right? So this is going to be the electric intensity at a point R from a charged cylinder. Fine, do we get this thing clear? Now if epsilon is the relative permittivity of the medium is relative permittivity of the medium, then I can say that epsilon will be equal to epsilon 0 k, in which case the electric intensity at a point r will be q upon 2 pi epsilon 0 k r, right? Now, if the cylinder is placed in vacuum, if the cylinder is placed in vacuum, then K will be equal to 1. So in that case, electric intensity will be Q upon 2 pi epsilon 0 R, right? Now, if the point is on the charge conductor, if the point is on the charged conductor or charged cylinder, if the point is on the charged cylinder, then R will be equal to capital R, in which case I can therefore say that electric intensity will therefore be E will be equal to Q upon 2 pi epsilon 0 K R, right? So these are the different formulas for electric intensity at different points or close to a charged conductor.
He will not come.
That is if it is placed in air. If it is not placed in air, I am considering the original formula and then doing it. Fine, do we get this thing clear? So this is electric intensity at a point outside a charged conductor, right? Next, let's consider the electric intensity. Let's try to find out what is the electric intensity.
Epsilon is relative permittivity of the medium.
So if epsilon is relative permittivity of the medium, relative permittivity of the medium is nothing but permittivity of air into K. Relativity of the medium is K times permittivity of air. So I'm substituting the value of epsilon as epsilon 0 K. For air, K is 1. So if I substitute K as 1, then this will become 2 pi epsilon R. Now guys, see this diagram.
That's vacuum, right?
Vacuum or air. For vacuum and air, K is 1. Right? And suppose, see this. This point P, instead of being near the charged cylinder, if it is on the charged cylinder, then what will the value of small r be? The value of small r and capital R will become same. So that is the last thing that I've done. Next, let's find out electric intensity at a point near a charged conductor. Let's consider a charged conductor of any shape, right? Let's assume that it is carrying a positive charge, right? Let's take a small area on the surface of the charged conductor. This is a small area ds I'm considering on the surface of a charged conductor. Draw a Gaussian surface. If I draw a Gaussian surface, since this is a circle, the Gaussian surface will be a cylinder right? Now, we have to find out the electric intensity by using this. I have a point P which is on the charged conductor. I have considered a small area ds around point P and I have drawn a Gaussian surface around it. Okay? Let's write these assumptions down. Let us consider a charged conductor of any shape. Let us consider a charged conductor of any shape, right? Now, the electric intensity at any point just outside the charged conductor, the electric intensity at any point just outside the charged conductor is just outside, the electric intensity at any point just outside a charged conductor is always perpendicular to the surface. Very simple, guys. The electric intensity is going to be given out this way. So the electric intensity obviously will be perpendicular to point P, so it will always be perpendicular to the surface, right? Now, this is because if it is not so, then the component of the intensity parallel to the surface of the, it will be parallel to the surface and will move along the surface. It will not move outwards, and this is contradiction to the supposition that if there is a charge, then the charge is always stationary. If it is not perpendicular, that means then it has to be parallel. If it has to be parallel, that means the electric intensity will move here, which shows that the charge moves on the conductor. But we know that charge is always stationary. Charge on a conductor, once I charge a conductor, that charge is going to be stationary. It does not keep moving, right? So that is the reason why it always has to be perpendicular to any point on the surface of the conductor. So long as the charges are stationary on the surface of the conductor, the electric intensity at any point outside the charged conductor must always be perpendicular to the surface. Do you understand why I have said they are perpendicular to the surface? Now, what will be the electric intensity inside the conductor? Can someone tell me what will be the electric intensity inside the conductor?
Negative.
Zero. Because there is an experiment called as Faraday's butterfly net experiment, which says that the charge inside the conductor is always zero. The charge always rests on the surface of the conductor. So I will write this down also, that also the electric intensity, electric intensity inside the conductor is zero, because a charge will always rest outside the conductor, right?
But where does the negative?
There's no, I've given it an external charge plus Q, right?
No, but there should be some charge to balance it.
Okay, I'll come to that. If, let's assume that what you all are saying is right? Let's assume that there is some charge inside the conductor also. If there is some charge inside the conductor, then that will constitute to movement of charge. If there is a positive charge or if there is a negative charge inside, let me hypothetically assume that what you are saying is right. Let us assume that there is a positive charge inside. Okay, let's assume that there is a negative charge inside. Hypothetically, let us assume that what you are saying is right. If there is a negative charge inside, we know that opposite charges attract. That will constitute, if opposite charges attract, one of the charge will have to move. That will constitute to movement of charges, which is contradictory to my supposition that charges are always stationary. That means the charge inside the conductor has to be zero. Only if the charge inside the conductor is zero will there be stationary charges. Okay, so everybody is clear with this point, that the electric intensity inside the conductor will also be zero, right? Now that our suppositions are clear, let us consider a closed surface formed by a cylinder. Let us consider a closed surface formed by a cylinder of area of cross section ds, right? Both its end being in plane. Okay, its ends being plane. Both the ends being plane and lying on either side of the conductor. Either side of conductor. Fine, do we get the thing there? Now, lying on either side of the conductor, ds is the surface area of the conductor around point P. ds is surface area of conductor around point P, right? So in which case around point P, and the cylinder encloses the area ds, and the cylinder encloses area ds, right? Now as we know that there is going to be no electric field inside the conductor, and the electric field which is outside the conductor will be perpendicular to the surface. Therefore I can say that since the electric field outside is perpendicular, that means I can say that the electric intensity inside is going to be equal to 0. The electric intensity inside the conductor is going to be equal to 0, right? So therefore I can say that total normal electric induction, the total normal electric induction over the closed cylinder, is going to be equal to epsilon E ds. The area I am considering around point P is ds. Now let us assume, let sigma be the surface density of charge. Let's assume that sigma is the surface density of charge. Now what do you understand by surface density? Surface density means charge per unit area. What is surface density? Surface density is charge per unit area. So that means I can say, therefore this is charge upon area. That's what is surface density. This is by definition. But area we have said is nothing but ds. Therefore I can say that the total charge on the conductor is going to be sigma times area, which is sigma times ds, right? So the total charge inside, not the conductor, sorry, cylinder, the total charge on the cylinder is going to be nothing but sigma times ds. Now by Gauss's theorem, Gauss's theorem states that the total normal electric induction is equal to the total charge, which is sigma ds, and we found out that total normal electric induction is epsilon E ds. Therefore I can say that epsilon E ds is sigma ds. ds gets cancelled, so I'll get E is sigma upon epsilon. That is going to be my electric intensity at a point near a charged conductor. Fine, do we get this thing clear? Now if epsilon is equal to epsilon 0 k, that is where epsilon is the relative permittivity of the medium, epsilon 0 is the relative permittivity of free space. This is relative permittivity of medium. This is relative permittivity of free space, and K is dielectric constant. Then I'll get E is sigma upon epsilon 0 k, right? But for air, K is equal to 1, so E will be equal to sigma upon epsilon 0. So this is going to be electric intensity at a point outside the charged conductor. Now if this is going to be my electric intensity at a point outside the charged conductor, let us find out the mechanical force that it will exert. If this is intensity, that means this has to exert some mechanical force. Let's try to find out mechanical force. Let's derive an expression for mechanical force on unit area of charged conductor. Let's try to find out the mechanical force on unit area of charged conductor. Let's consider a conductor of any shape, right? Let us consider a point P on the conductor. Let us consider a small area ds around point P, right? Now, let's assume that there is positive charge on the conductor. Now we know that the electric intensity is always perpendicular to the given point, right? That means the electric intensity, if I consider let's consider point A just outside, let's consider point B just inside, right? Okay, now let's first just write these assumptions down. Consider a charged conductor of any shape. Consider a charged conductor of any shape. Consider a charged conductor of any shape in a medium of dielectric K. Medium of dielectric K. Right? Now consider a small surface area ds on the conductor. Consider a small area ds on the conductor. Right? Now, let's also assume that sigma is the surface density of the charge on area ds. Sigma is surface density of charge on ds. Right? Now, in that case, we have just derived that electric intensity at a point just outside the conductor is electric intensity. We just derived that electric intensity just outside a point of a conductor is sigma times epsilon 0 K. Right? Now, this intensity we also have discussed will act in a direction perpendicular to the surface. This intensity acts in a direction perpendicular to the surface, right? Now, the intensity can be considered as a resultant of two intensities. The intensity that will be given out, this intensity can be considered as a resultant of two intensities. Now, what are the two intensities? One, the intensity E1 due to the charge on area ds. Intensity E1 due to the charge on area ds. Right? So, in that case, E1 due to the charge on ds, now this is a three-dimensional point, so this will exert a force E1 outside and this will exert a force E1 inside. Right? If I have just a point, obviously the point is going to exert a force on both the directions. Right? So it is going to, that area ds is going to exert a force outwards as well as inward. Next, the second force that will be generated is intensity E2 due to the charge on the remaining surface of the conductor. Intensity E2 due to the charge on the remaining surface of the conductor. Now, the charge E2 is due to the remaining surface of the conductor. Now, conductor is a three-dimensional figure. We just discussed that there is no charge inside the conductor. That means, since there is no charge inside the conductor, both the E2s are going to act in outward direction. Since charge cannot remain inside the conductor, both the electric intensity due to the charge on the conductor are going to act in outward direction. That means the total intensity is going to act in outward direction, whether it is inside the conductor or outside the conductor. That force is going to be directed in outward direction. Now, there, and I can say that the total intensity E is a sum of E1 plus E2. The total intensity E is a sum of E1 and E2. Yes, you want to ask me something?
Something. Point P is the energy released by point P. I mean, a charge.
Like number of lines of force per unit area.
Is divided in E1 and E2.
E2, right?
So E1 is being projected.
The total force at point P will be due to the seat. If there is one body here and there are a body here. And this is going to give you some lines of force. And this is also going to give you some lines of force. So the net resultant of this is due to this small area and due to the remaining area. Fine, do you get this thing clear? Okay, let's move on ahead. Now, intensity E1 due to the charge is directed on both sides. Intensity E1 due to charge on ds is directed on both sides, right? Both sides, but intensity E2 due to the charge on the remaining surface of the conductor, but intensity E2 due to charge on remaining area of the conductor is directed outwards only, is directed only in outward direction, right? Now, the resultant electric intensity at any internal point B, now inside the conductor, the resultant intensity at any point, let's consider that point as B, inside the conductor. Now inside the conductor, as we can see that E1 and E2 are in opposite direction, therefore the resultant intensity inside the conductor will be E1 minus E2, right? And but we know that there is no charge inside the conductor, but there is no charge inside the conductor. That means the total intensity inside the conductor should be 0. That means I can say that E1 minus E2 should be equal to 0. Hence, I can say that E1 should be equal to E2 inside the conductor. If I substitute this in equation 1, guys, can you just see this? This was my equation 1. Total intensity E is nothing but E1 plus E2. E is equal to E1 plus E2. Therefore, I can say E is equal to twice E1 because E1 is equal to E2, right? Now, E we have already found out. We already said that this is equal to sigma upon epsilon 0k. E is equal to sigma upon epsilon 0k. Right in the beginning I had said, guys, E is equal to sigma upon epsilon 0k. Therefore, I can say that 2E1 is equal to sigma upon epsilon 0k. Hence, I can say that E1 is equal to sigma upon 2 epsilon 0k. I'm taking 2 in the denominator. If E1 is this, I can say therefore E2 will also be equal to sigma upon 2 epsilon 0k. Right? Now, that means this is going to be my electric intensity E1 and E2. Now outside the conductor, both are in the same direction. At any point A, E1 and E2 act in the same direction, right? Now let us assume that F is the force that acts on area ds. Now I can say that any charge, the charge on area ds, the charge on area ds placed in an electric field of intensity E2, which is produced by the area of ds on the remaining charge of the conductor E2. Let's assume that the charge on area ds placed in an electric field of intensity E2 produces a force F and a force F acts on area ds, right? Obviously, if you have, guys, try to understand this was my area ds, this is the point P. Here you have a remaining conductor. The remaining conductor will not only exert a force, will not only exert electric intensity at a point outside, but will also exert an electric intensity on this area ds. This conductor is going to exert a force at point P, and this conductor will also exert a force on this area ds. Let's assume that the force that it exerts on area ds is F. Now in that case, I can say that F is equal to charge on ds multiplied by intensity due to the remaining charge. Intensity due to remaining charge. Right? So force is charge on ds. We found out charge on ds to be nothing but total charge is charge density into area. So charge on ds is going to be sigma ds. Intensity due to the remaining charge is nothing but E2. So this is sigma ds into E2. E2 we found out is nothing but sigma upon 2 epsilon 0 k. Hence I can say that the force exerted is sigma square ds upon 2 epsilon 0 k. Right? Now this force, this is the force that is going to be acting on area ds. Therefore, what will be the force acting per unit area? Force, let us assume force small f acting on unit area of the charge conductor will be nothing but small f is going to be capital F upon ds. So therefore this will work out to be sigma square upon 2 epsilon 0 k. That will be the force per unit area, right? But we had already derived that electric intensity is sigma upon epsilon 0 k, right? Therefore I can say that sigma is equal to E times epsilon 0 k, right? If I substitute this value of sigma, I'll get therefore force per unit area is E times epsilon 0 k the whole square upon 2 times epsilon 0 k, right? So this is going to be equal to E square epsilon square K square upon 2 epsilon 0 K. Epsilon 0 square gets cancelled, K and square gets cancelled. This is half E square epsilon 0 K. Right? So the force per unit area is going to be half E epsilon 0 K E square. That is going to be the force that is going to be exerted by a small area ds. Right? If this is, yeah, this force, the formula for total force is nothing but charge on ds multiplied by intensity. Charge is nothing but, what is charge density? Is nothing but charge upon area. So charge will be equal to surface density into area. That's how I got the charge. And then the intensity due to the remaining conductor is E2. That means a charge is going to produce force. If it is going to produce force, that means it will also produce displacement. Force and displacement will produce work. Work will give rise to energy. Let's find out the energy. Next, let's find out the energy density. Energy density of a medium. Now, whenever a charge is given to a conductor, an electric field is produced in the medium which surrounds the conductor. See, charge given to a conductor produces an electric field in the area surrounding the conductor. Right? Now, during charging, the charge is brought to the conductor and therefore some work must have been done in charging the conductor. This is my conductor which has no charge. There must have been some charge which must have been brought from infinity to this conductor to charge this conductor. That means some work must have been done in bringing the charge from infinity to the conductor so that the conductor can be charged. Right? So I can say that during charging, the charge is brought to the conductor. Charge is brought to the conductor. Right? And therefore work is done during charging the conductor. Therefore I can say that some work is done in charging the conductor. If some work is done in charging the conductor, the work done on charging the conductor remains stored in the electric field that is surrounding the conductor in the form of electrostatic energy. This work that is done, this work done remains stored. The work done remains stored in the electric field. The work done remains stored in the electric field in the form of electrostatic energy. Form of electrostatic energy. Right? Thus, there will always be energy that will be stored in an electric field. Therefore, an electric field will always have some energy. Therefore, I can say that energy always remains stored. Always remains stored in the electric field. Right? So do you understand why there is energy in an electric field? Now we have already derived that mechanical force per unit area, mechanical force per unit area, F is given by the formula half epsilon 0 k E square, right? Therefore, I can say that total force F will be nothing but mechanical force per unit area into area ds. So in that case, this is going to be nothing but half epsilon 0 k E square into ds. That will be the total force F. Now, we know that if the area ds is moved by a distance, say dx, if area ds is moved by a distance dx, right, against the force, then work done, since I'm moving the area ds by a small distance, small work is going to be done. Work is defined as the product of force and displacement. Work is force into displacement. Force is F, displacement is dx, right? We already know the value of F, we also know the value of dx. So therefore I can say that work done dw is equal to F can be written as half epsilon 0 k E square ds into dx, right? Area, ds is the area, dx is the length. Area into length is nothing but volume. Therefore I can say that work done is half epsilon 0 k E square into dv, right? So this is going to be the work done. This work done is stored in the volume in the form of potential energy. Work done is stored in the volume in the form of potential energy, right? Therefore, I can say that energy stored per unit volume, energy stored per unit volume, we will call this as energy density, is equal to energy density, and it is represented as capital U. Therefore, I can say energy density is work done per unit volume. Work done we just found out as half epsilon 0 k E square dv upon dv. Therefore, I can say energy density is half epsilon 0 k E square. So that is going to be the energy that is going to be stored due to the charge in the conductor. Next, let's understand what is the concept of a condenser. Let's try to understand the concept of a condenser. Now, every conductor has a definite capacity to hold a charge. The ability of a conductor to hold a charge is called as the capacity of the conductor. Every conductor has a capacity to hold charge. The capacity of the conductor, or the ability of the conductor, the ability of the conductor, the ability of the conductor to hold charge is called capacity of conductor. Fine. Now, if this is, that means in simple language, how much charge can be stored on a conductor is your capacity of the conductor. Now, what are the factors on which capacity of conductor depends? Factors affecting capacity of conductor. The factors affecting capacity of conductor are: first, the shape and size of the conductor. Second, the nature of the surrounding medium.
Why have you written condenser?
Condenser and see, capacity of conductor or condenser is the same thing, right? Now, shape and size of the conductor, nature of the surrounding medium. Next, presence of other charged body near the conductor. Presence of other charged body near the conductor. Right? So these are the three factors that determine how much charge will it hold, a conductor hold. Charge held by a conductor, or that is also called as capacitance of a conductor. Fine, do you get this thing here? That means when a conductor is given charge, its potential will increase. If there is a charge on it, that will give rise to some potential. Therefore, I can say that the charge on the conductor can be written as directly proportional to the potential. When charge is given to a conductor, its potential increases. Therefore, I can say that charge on conductor is directly proportional to potential. That means I can say Q is directly proportional to V. Therefore, I can say that Q is equal to CV, where I can say C is a constant. And this constant C is called as electrical capacity or capacitance. Is called electrical capacity, right? That means I could therefore say that C is equal to Q upon V. Simple basic algebra. That means I can say that capacity is the ratio of charge upon potential. Fine. Hence, I can say that the capacity of a conductor can be defined as the quantity of charge required to raise the potential by 1 unit. Definition. Capacity of conductor can be defined as the quantity of charge required to raise the potential by 1 unit. Raise potential by 1 unit. If this is the capacity of the conductor, that means what will be the unit of capacity? The unit of capacity is going to be equal to unit of capacity. The unit of capacity will be nothing but the unit of charge upon unit of potential. Unit of capacity will be nothing but unit of charge upon unit of potential. Right? Unit of charge is nothing but coulomb. And unit of potential is nothing but volt. Therefore, unit of capacitance is nothing but coulomb upon volt, and coulomb upon volt is called as farad. Right? Thus, the unit of capacitance is 1 farad. Fine, do we get this thing clear? How do I define 1 farad? 1 farad is the amount of charge required to raise the potential by 1 volt. Right? Okay, we'll stop this here for the day. Thank you very much.